need to inspect what tools your MCP server actually exposes before calling them. We'll use FastMCP's list tools to fetch every available tool, then examine their names, descriptions, input schemas, and even custom metadata tags, so you know exactly what's callable and how to use it.
Async with client. Tools equals await client list tools. Hash tools list MCP, types, tool. For tool and tools. Print F tool, tool name. Print F description, tool description. If tool input schema. Print F parameters, tool input schema. Hash access tags and other metadata. If hasheader, tool, meta and tool meta. FastMCP meta equals tool, meta get FastMCP. Print F tags, FastMCP meta get tags.
This demonstrates the metadata-driven discovery pattern for dynamic tooling systems. The code shows how FastMCP exposes executable functions as first-class tools, complete with introspection capabilities that reveal names, descriptions, schemas, and custom metadata. What makes this distinctive is the dual-layer metadata system, where standard MCP fields coexist with FastMCP's namespaced extensions for tags and other framework-specific attributes. The pattern works by treating tools as self-describing entities rather than opaque endpoints. Clients discover available tools through a standardized interface, then access both structural metadata, like input schemas, and arbitrary key-value pairs, like tags, through a unified object model. This design enables declarative filtering and categorization without requiring server-side changes, as metadata travels alongside the tool definitions themselves. This approach solves the common problem of tool sprawl in extensible systems. By making tools discoverable and categorizable through metadata, you eliminate hard-coded tool registries while enabling dynamic client behavior like tag-based filtering or context-aware execution. The trade-off is slightly increased payload size for metadata, but the flexibility gain, especially in AI agent systems or plugin architectures, justifies the overhead when you need runtime adaptability. Let's break it down line by line.
Async with client.
Async context manager pattern ensures the FastMCP client connection is properly initialized and cleaned up, even if an error occurs during operations. Critical for resource management in async environments.
Tools equals await client list tools.
This fetches the complete list of available tools from the FastMCP server. The await handles the async operation, ensuring non-blocking execution while retrieving the tool registry for inspection or dynamic routing.
Hash tools list MCP, types, tool. For tool and tools.
This iterates through each tool in the tools list, where each item is a strongly typed tool object from the MCP client. The loop processes every registered tool, enabling inspection of their names, descriptions, and schemas for dynamic tool discovery.
Print F tool, tool name.
This prints the tool's name from the tool object, providing immediate identification in the list output. Critical for debugging and verification when working with multiple tools, as names uniquely identify each tool's functionality.
Print F description, tool description.
This prints the tool's description to the console, providing human-readable documentation about what the tool does. Critical for debugging and discovery when working with AI-callable tools, as it surfaces the natural language explanation that models use to understand tool capabilities.
If tool input schema.
This conditional checks for the presence of an input schema before attempting to print it. Tools without schemas are valid, so this prevents attribute error while maintaining flexibility for schemaless operations. The pattern handles optional attributes safely, a common requirement in dynamic tooling systems.
Print F parameters, tool input schema.
This prints the tool's input schema, which defines the expected parameters for AI invocation. The schema acts as a contract between the tool and AI models, ensuring proper argument structure and type safety.
Hash access tags and other metadata. If hasheader, tool, meta, and tool meta.
Defensive attribute access checks if the tool has a meta attribute and that it's non-empty before proceeding, preventing attribute error crashes. This is the safe access pattern for optional metadata fields.
FastMCP meta equals tool, meta get FastMCP.
This safely accesses FastMCP-specific metadata through the tool's meta dictionary. The get FastMCP pattern handles missing keys by returning an empty dict, preventing key error while maintaining clean access to custom metadata fields.
Print F tags, FastMCP meta get tags.
This safely accesses tool tags from the FastMCP metadata dictionary, using an empty list as fallback if the tag's key doesn't exist. The get pattern prevents key error exceptions while maintaining clean output, ensuring the code handles missing metadata gracefully. FastMCP tool discovery pattern. This metadata inspection loop demonstrates how FastMCP clients dynamically discover and introspect server-side tools, exposing their schemas, tags, and capabilities without prior knowledge. The FastMCP namespace in tool metadata is optional and server configurable, so always check for its existence before accessing tags. This pattern enables clients to adapt to evolving server capabilities without hard-coded dependencies.
The client that knows nothing about the tools can use all of them.